You know, we often think of math as just a bunch of rules and numbers, but what if it's actually a language? Today, we're going to get bilingual. We're learning two completely different ways to talk about the exact same spot: polar coordinates and rectangular coordinates.
Seriously, think about it. If you're giving a friend directions to your house, you could say, okay, go 3 blocks east, then 4 blocks north. Or you could just point and say, it's 5 blocks, that way, right? Both get your friend to the same place, they just describe the journey differently. That's exactly what we're diving into today.
So here they are, our two languages. On one hand, you've got rectangular coordinates, the good old x, y you've known for years. It's the over and up method, kind of like walking along a city grid. On the other hand, we've got polar coordinates, or r, theta. This is the distance and angle method. How far do you go? That's r, and in what direction do you turn? That's theta. Think of it as a direct flight path.
All right, so how do we actually translate between these two languages? Well, like any good translator, you need a dictionary. And for us, that dictionary is our conversion toolkit, built on 4 absolutely essential formulas.
And here it is. This is our Rosetta Stone for real. To go from polar to rectangular, we're just using some basic trig. Your x value is the radius times the cosine of the angle, and the y value is the radius times the sine. Simple. Going the other way, from rectangular to polar, we use the Pythagorean theorem to get that direct distance r, and then the tangent function to figure out the angle theta. These 4 little formulas, they're the bridge connecting both worlds.
Now hold on. Before we go any further, I need you to burn this next piece of advice into your brain. It is the single most important tip in this whole explainer. You have to know which quadrant your point is in. Why? Because your calculator, bless its heart, can sometimes lie to you, or at least not tell you the whole story. Seriously, a quick sketch is your best friend here. So here's the deal. When you hit that inverse tangent button on your calculator, the arctan, it's programmed to only give you an angle somewhere between -90 and +90 degrees. That's great for quadrants I and IV. But what if your point is in quadrant 2 or 3? Well, the calculator gives you something called a reference angle. To get the real angle, you have to step in and manually add pi, or 180 degrees to it.
All right, theory's great, but let's get our hands dirty and see how this toolkit actually works. We're going to walk through 3 examples, starting simple and then leveling up to something a little more complex. First up, a classic polar to rectangular job. We're given a point that's a distance of 2 from the center and an angle of pi/3. Our mission is to find its xy address on that city grid.
This direction is usually the easier one. You just plug the values straight into our formulas. For x, we get 2 times the cosine of pi/3, which is just 1. For y, we've got 2 times the sine of pi/3, which is the square root of 3. So boom, our rectangular point is 1, square root of 3. Easy as that.
Okay, now let's go the other way. We're given the rectangular point -√3, -1. Now notice right away, both x and y are negative. That's a huge clue. It's screaming at us that this point lives down in quadrant 3.
Let's just follow the steps. First, we find r with Pythagoras. So r squared equals -square root of 3 squared plus -1 squared. That all works out to 4, so r is 2. Next, the angle. The tangent of theta is -1 over -square root 3. Your calculator will tell you the arctan is pi/6. But wait, that's in quadrant 1. Since we already know our point is in quadrant 3, we have to do our critical step. We add pi to that reference angle, which gives us the correct angle of 7 pi/6. See how important that quadrant check was?
All right, for our last example, we're leveling up. We're moving from single points to entire equations. The challenge? Figure out what the polar equation r equals 4 cosine theta actually looks like in the rectangular world. This is where things get really cool. At first glance, this looks kind of tricky, but here's the secret weapon. You multiply both sides by r. That one simple move gives you r squared on the left and 4 times r cosine theta on the right. And just look at that. We have perfect things to substitute. R squared becomes x squared plus y squared, and r cosine theta becomes x. From there, we do a bit of algebra, using a neat trick called completing the square to rearrange things, and get it into a standard form we all recognize.
And here is the big reveal. That simple, elegant little polar equation, r equals 4 cosine of theta, is just a perfect circle. It's centered at the point 2, 0, and it has a radius of 2. This is a great example of how sometimes polar coordinates can describe things like circles way more simply than rectangular coordinates can.
So, we've seen how to get things right, but let's take a second to talk about the 3 most common traps that people fall into just so you can sidestep them like a pro.
Okay, first, and I know I sound like a broken record, but it's blindly trusting your calculator's arctan result without checking the quadrant. Don't do it. Second, when you're converting equations, it's so easy to forget that clever first step of multiplying by r to create terms you can actually work with. And last, just remember that r can technically be negative, it just means you walk backwards. But for simplicity, we almost always use the positive value.
So why are we learning all this? Is it just for a math test? Absolutely not. This skill, translating between coordinate systems, is actually humming away inside the tech you use every single day.
I mean, just take your phone's GPS. Satellites in space are pinpointing your location using the 3D version of polar coordinates. Think latitude, longitude, and altitude. But the map on your screen? It's a flat, rectangular grid. And the math that translates between those two systems is happening in real time, right in your pocket.
Yep, every single time you ask for directions to the nearest coffee shop, there's a whole system built by engineers that is constantly translating between these coordinate languages to draw that little blue line on your flat map. It's a direct, really powerful use of the exact math we just covered. So, we started this whole thing by saying math is a language. Well, you can now describe any spot on a 2D plane using two different dialects. You can translate between them. The real question is, what new problems can you describe, and what new solutions can you find now that you're bilingual?